Yeah. Uh, Hello, everyone. I'm Yidi, and I'm working in. I'm a postdoc working at CE, and this work was uh, done under the help of our Philip, Willie, and other colleagues. And today, I would like to talk about the secondary foresting in boreal region from the satellite data. Um, Um, our study focused on the boreal region where the fire numbers and the fire area is increased, since the wildfire has led to large amount of forest loss and degradation in boreal region, and we have a limited knowledge about the amount and the distribution of carbon lost. So our objective is to quantify the biomass loss and the recovery from fire disturbance in boreal region using high-resolution satellite data and bookkeeping model. Here we propose a framework of our work. We first use a Landsat-based fire history datasets named Gabon to derive the forest age maps. And then we combine the forest biomass map and then using the space for time method to establish the relation between the biomass and the age, and the recovery curves were calculated over each 1 degree forested grid boxes. And then combining the burn area history, we will further calculate the secondary carbon sink and emissions. The carbon budget here includes the gross sink from the secondary forest burned after the 1985, the carbon sink before the 1985, the fire emission at the time of fire disturbance, and the decay from the coarse woody debris. Here we show an example of the fire disturbance map from Gabon and the two biomass datasets. The deeper color here refers to fire disturbances in the earlier year, while the lighter one shows a fire in recent years. This one is in generally consistent with the higher biomass value in the two biomass datasets. But we also can see there is a differences from these two biomass maps with higher value in CCI biomass maps. Here is an example of the fitted recovery curve in different grids. Here we test the different functions and applied the Chapman-Richard function, which is more flexible in shape. Here we can see the exponential shape and the S shapes here. From this function, we could derive the equilibrium HB and the recovery time. We also fitted two lines in every 1 degree grid using the HB and H from the regions with frequent fire and occasional fire. So we can derive the two lines here. Here we presented our fitted regional biomass recovery curves. Here we divided the boreal region to 3 subregions, the North America, West Eurasia, and East Eurasia. And we could see that the boreal forest in Eurasia, the green line color, reaches higher equilibrium HB than the boreal forest in the North America, the blue line. In this figure, we show the spatial distribution of the equilibrium HB and the recovery time. From the comparison by the CCI biomass and the SACHIS biomass data sets, both two data sets have a similar equilibrium HB, but the Sessons map reaches higher recovery time. And for the validation, we collect more than 100 kernel sequence sites with more than 1,000 observations. And we can see that in some lines here, our recovery curve is very similar to the observations. And the overall, the mean R square of the fitness is around 0.5. And we also compare the HB recovery rate for the young fire recovered forest. We find a good fitness in the HB recovery rate by the frequent curves. Here is a preliminary estimate of the secondary forest sink rate and the emission after fire disturbance. Here is the mean sink rate for the fire regrowth forest from 1985 to 2020 was around 0.35 megacarbon per hectare per year, while the emission rate is nearly the half, and it is also comparable with median GFAT emission values. But we can see there is some difference between the in the spatial patterns. This is mainly because that the burned area is different from the GFAT and the carbon dataset. We further calculated the secondary carbon budget here. The total secondary forest sink from 1985 to 2020 is around 0.4 to 0.7 kg per carbon, and the emission is around 0.3. And there you can see the great contribution of the occasional fire region, and the biggest net sink in the East Eurasia, and while the North America is a net emission here. It is mainly it is probably because the crown fire is dominated in the North America, while the surface fire is more often in the Eurasia. And here is the temporal variation of the carbon balance. And in the budget above, we didn't add the cost-wooded debris yet, but we should notice that the fire disturbance would also cause the changes in the ratio between the live biomass and the dead biomass pools, like this conceptual figure shows. The fire forms cost-wooded debris would represent a significant component of forest carbon stocks, and the decomposition rate would also cause the carbon emissions. Here we'll show the different decomposition curves, and this may have the large impact on the cost-wooded debris pool changes. Meanwhile, we also calculate the ghost sink here from the pre-satellite disturbance epoch and the other disturbances. The ghost sink from the 1985 to 2100 is around 24 pecarbon, and is dominated in the southern part of Eurasia. Finally, we also applied the random forest to explore the potential environmental drivers on equilibrium AGV and the recovery time. And from the important ranking, we found that GPP is the most important variable influencing the equilibrium AGV, while the species composition is more important for the recovery time. And our further work would be extended the analysis from boreal region to global area, and also to explore the differences from the other disturbances such as harvest, drought, insect, and windstorms. Thanks. I will end up here.